Well, I'd like to be able to introduce at this point to you Dr. Matthew Szydagis. Uh, Matt is a very energetic, passionate researcher into a world that many of us have maybe not heard of or certainly have never seen. I don't think I've ever seen any dark matter. In fact, it's pretty much invisible, I guess, as far as I'm concerned. Uh, Anyway, I'm not talking about UFOs or UAPs here. I'm referring to dark matter. One might ask how dark matter has any relevance to UAP. Matthew's here to explain it. Uh, Dr. Matthew Szydagis received his BA and MS and PhD degrees from the University of Chicago, then worked as a postdoctoral scholar at the University of California, Davis. He's now an associate professor at the University of Alabama, SUNY, studying basically experimental particle and astrophysics, in particular, direct detection of dark matter, as well as general detector development for rare event searches. He was inspired by Star Trek, The Next Generation, as a child to become a scientist, and has always been fascinated by the UFO or UAP phenomena, treating it seriously his entire life. Matthew is also an SCU member and a science and technology consultant in dark matter and radiation detection for UAP expeditions. His presentation title is "What is the possible connection between UAPs and dark matter?" Matthew, welcome.
Thank you for your very kind introduction, Rich. And I want to make sure, right, technology is cooperating. You can hear me and see me fine?
You are coming in loud and clear. I see you very well.
Beautiful, beautiful. So now the next step is let's make sure the screen share is working, right? So it worked before. Let's make sure we can see my slides now. Is it, can you see my PowerPoint now? Is it full screen, Rich?
Yes, it is.
Beautiful. And I can move between slides and it's working?
And it's working fine. You're
excellent.
All right. We won.
Good. All right. So I'm very happy to be here to talk to you all today. And thanks again to Rich for organizing this very wonderful, open-minded, and intellectually stimulating conference this weekend. So today I'm going to be talking to you about what I do is search for dark matter and then see what possible connection there could be with UAP studies. So I'm going to be talking to you today about the invisible universe that we already know that is out there, even in mainstream science. So how did I get interested in science in the first place? As Rich mentioned, so I'm not old enough for the original Star Trek, but I did grow up watching Star Trek Next Generation. Came out around when I was in preschool age, kindergarten. I watched all 7 seasons of Next Generation. I never got into Deep Space Nine really, but then I did start watching Voyager, Star Trek Voyager, Captain Janeway, and her adventures when Star Trek Next Generation ended. And it really, even though it's fictional, this fictional universe inspired me to become a real scientist. I was inspired especially by Lieutenant Commander Data on Star Trek Next Generation as the dispassionate, science officer. And that really got me interested in science. And I think I was also sort of acculturated by Star Trek into thinking that, alien species and a federation, stuff like that. Oh yeah, certainly that's all real and we'll get there someday as humanity and discover the evidence to our alien stuff. It sort of acculturated me to humans working together as one, combined human race and alien races being out there. Also then in fourth, fifth, and sixth grade, I read some of these books like Hyperspace by Michio Kaku, who many of you know, The God Particle by Leon Letterman. And I also, another very formative book for me was Black Holes and Time Warps, Einstein's Outrageous Legacy by Kip Thorne, who recently shared the Nobel Prize with several other physicists for the discovery of gravitational waves. So these are some of the formative books and movies. Now, for me, in terms of the phenomenon itself of UFOs and UAPs, I don't have it on this slide, but I should add, I also read a book about UFOs from Isaac Asimov's Learning Library. I've got to find an image online one of these days of the cover of that book, which had a group of cows looking up at a flying saucer being struck by lightning. It was meant to be the ranch for Roswell. That was another great formative book for me, and it talked about also J. Allen Hynek and his classification of close encounters and things like that. And to me, I didn't see that as bad or pseudoscience. I read that just as much as I read these books here. So now let's talk about my field of research on dark matter, starting with a historical perspective. Where does the story start? So there are some very prominent astronomers, astrophysicists going back many years. So the story starts actually in the 1930s on the left here with Fritz Zwicky, who was a Swiss astronomer who found out, looking at galaxies, clusters of galaxies, particularly the Coma cluster, that the galaxies had too much energy, too much kinetic energy. They're moving around too fast. They had too high velocity. The cluster should have come apart, fallen apart. But so he hypothesized that there was extra matter in the universe that we didn't see. And he called this dark matter. However, this was laughed at for many decades, not really considered seriously by other scientists until the 1970s, when we have Professor Vera Rubin on the right. She recently passed away. Just a couple of years ago, she was in her 80s, and she more than just resurrected this work. It really took off with her when she found really additional evidence corroborating Fritz Zwicky's work. So what did Professor Rubin actually do? So she was the one who looked at the famous what are called rotation revolution curves. So when we look at stars as they're revolving around centers of galaxies, so in every galaxy, stars go around the center of the galaxy, just like how planets in our solar system go around the sun. But when you look at the so-called rotation or revolution curves, instead of the velocities of stars going around centers of galaxies falling off, they're actually increasing or asymptoting, flattening or even increasing in many cases with distance from the center of the galaxy instead of decreasing. Now, we would expect a decrease. Why would we expect a decrease? If you look at our own solar system, the farther away a planet is from the sun, the more slowly it orbits around it. And that's simply a result of the gravitational field falling off as 1 over the distance squared, which should result in the velocity mathematically falling off as 1 over the square root of the distance. So the farther away you are in square root of the distance from a center of mass that is producing a gravitational force, you should be seeing a decrease in velocity. And we do not see that when we look at galaxies. This does not seem to work on galactic scales. And one way we can explain this is by postulating there is extra mass. We call this the dark matter halo that we add to the matter that we call the disk. So that's ordinary matter like stars. And we sum those two components together, we do come up with an explanation that seems to match the data. And we can look at data very far beyond where we actually see starlight, because we can actually use what's called the 21 centimeter line of hydrogen and be able to look out to where there are very few stars, and we can look at the gas and dust in the outermost regions of galaxies like our own, and continue taking more data points to continue this chart out, this graph, to even greater distances in parsecs, kiloparsecs, and still we see the same trends. So by itself, this does not say that there's extra matter, because maybe we just don't understand the law of gravity and we need to modify our equations of gravity, which can equally well explain this data. But the thing is, is that for proponents of modified gravity in my field of dark matter are almost treated like, it's kind of funny, like dark matter debunkers. It's really funny because actually, if you live in the 1970s and 80s, you can explain away these graphs. However, there's a great deal more evidence than just the rotation curves are just the tip of the iceberg for dark matter. So if we look at the X-ray emissions of hot gases between galaxies. So now we're looking in between galaxies. We're not looking inside of galaxies. We see, so if we look inside of galaxies, the galactic rotation curves are consistent with a spherical halo of this dark matter. But if we look between galaxies, we have gases being held together despite there not being sufficient gravitational force from the star, from all these galaxies in this galaxy cluster. So we can combine X-ray data with visual data. What's binding those galaxies in place to make those X-rays considerably outside of these different galaxies? So Michio Kaku in one of his specials refers to dark matter as like the force in Star Wars that binds us together with its gravitational field. It's binding all these gases together. Even this, though, is still not sufficient evidence that there's new matter or new mass. You could still explain this by saying we don't understand the law of gravity, either relativistically or non-relativistically. So we still have to dig deeper. And we dig deeper by looking at something called gravitational lensing. So just like your eyeglasses or your contact lenses, gravity bends light. And the bending of light by gravity allows you to calculate how much mass is doing the bending. And when we perform that calculation, what we find is in agreement, both qualitatively and quantitatively, with the other studies. The rotation curves and everything agrees that there is unseen matter producing additional gravitational force. So what happens when we're looking at distant galaxies is that if there's an intervening galaxy or cluster of galaxies, so that's significantly more mass than one lonely galaxy there, what we see is the distant galaxy, if there's an intervening mass of a cluster of galaxies, what we see is called gravitational lensing, where a galaxy is distorted. And you see this down here. This is a cartoon, but in the lower left, you often see the same galaxy duplicated multiple times, twisted. It's like looking through, a wine glass or champagne glass distortion of light. And what's really interesting is that, as I said, you can calculate, these are incredible masses. You have a cluster of galaxies, and each galaxy is harboring a supermassive black hole in its center, which is the center of every galaxy. And so there's a lot of mass here. You have trillions upon trillions of stars within these galaxies. So you have a distortion of light, and that distortion of light allows you to calculate how much matter there is. So as far as I've been able to see, these gravitational lensing studies, this cannot be explained by modifying gravity. You can't explain away these. So when you combine gravitational lensing with the rotation curves, you're almost forced into a model where there is more matter, there is more mass. There's something extra out there that is not accounted for, that's shining within stars, luminous matter, and galaxies. And sort of what's considered by many the nail in the coffin for ideas of modifying gravity is the bullet cluster. So the bullet cluster is actually, on the right here, is a picture of a collision between two galaxy clusters where we have three images overlaid here: the optical, gravitational lensing in blue, and hot X-ray emitting gases again in pink. And none of those match. The centers of mass, the centers of these blobs in pink, blue, and the visual centers here, none of them line up. The center of mass as calculated from visible matter from stars, visible matter from gases, and the gravitational lensing map that's created in blue, so that's using this gravitational lensing. None of those line up. But if you postulate that you have an invisible matter that does not participate in the collision in the center of the image, but kind of slips out of the central collision between these two galaxy clusters and creates these two lobes here, then you can explain this data and you can explain this image. And I should emphasize, to give you the scale here, these are not stars in this image. There are a couple, nearby stars that get into the image. Most of the fuzzy splotches you see in this image are not stars. They're galaxies with hundreds of billions of stars. You are looking at clusters of galaxies on the right. You are not looking at individual stars. So this is a cluster. There's a cluster on the left and a cluster of galaxies on the right that is colliding and mixing over billions of years. And the bullet cluster is itself about 1 gigaparsec away, so it's over 1 billion light years away. So because of the finite speed of light, this collision between two galaxy clusters has already happened. We're seeing it happening through our telescopes 1 billion light years away, 1 billion years back in time. So the story still doesn't end there. We also we want to calculate, okay, what fraction of the universe is made of dark matter than per galaxy per unit volume. So there isn't one more thing we look at, which is called the CMB, the cosmic microwave background. So the CMB, or cosmic microwave background radiation, which was discovered in the 1960s by accident, actually, by Penzias and Wilson, who thought there was bird poop on their antennas, on their microwave and radio antennas, actually made one of the biggest discoveries in cosmology, which is this pixelated map right here, variations in temperature in the sky. So the cosmic microwave background is sort of an echo from the Big Bang. It's a residual radiation from the beginning of time caused by the universe cooling down. And these little orange and blue pixels you see here, these are tiny variations in the temperature of the sky effectively. So the average temperature is 2.7 Kelvin, which corresponds to microwave radiation. But that's just an average. There are very small sub 1% level variations. And if you look at the clumpiness in those variations, you can make a chart like this one. And then the peaks in the spatial clumpiness of the radiation tells you the amount, different types of matter and energy that make up the universe, and what fraction of the universe is made of those different percentages. And so this allows you to put together what's called what we can call the cosmic detective story, the case of the missing mass and the case of the missing energy. When we look at the cosmic microwave background, we can create this pie chart. And this pie chart shows that 25% of the known universe is dark matter. 69% is this other thing called dark energy, which will be the second half of my talk. Actually, first half of my talk only is about dark matter. Mostly going to talk about this huge percentage here. And then there's atomic matter, which is 5%. And so you might be thinking, does that mean we only understand 5% of the universe? Oh, it's much worse than that. Because of that 5%, 3/4 of that 5% is hydrogen. 1/4 is helium. So you heard that right. That means that oxygen, carbon, silicon, the entire periodic table, and all the elements responsible for life like carbon, oxygen, nitrogen, they're the sub 1% dregs of the universe. They're not even important enough to show up in this chart. The atoms inside of you and me are so rare. They come from supernova explosions over the last few billion years, and neutron star collisions and other astrophysical processes seed the universe with this life-giving material. But that life-giving material is a tiny, tiny, tiny fraction of atoms even. So what we understand of the universe, all of physics, chemistry, biology, is a tiny fraction. So the point I always make with this pie chart is it's the height of hubris to think we understand everything. We understand very little. We're making some headway on what dark matter is, and I'm going to talk about the headway being made on what dark energy is, but we still have no idea what either of those are. We know something's there. Why do we know dark matter is there? Because it makes an imprint on the cosmic microwave background. And I mentioned earlier rotation curves and gravitational lensing. So that's how we get this 25% here in red. And then this black chunk in 69%, we get that also from the studying the cosmic microwave background. So dark matter produces a positive gravitational force like ordinary matter, pulls things together. Dark energy, we have no idea what the hell that is pushing things apart. It has an anti-gravitational-like effect, and we have no idea what really is causing that. And it's pushing the universe apart faster and faster and causing an increase in acceleration. Now, this pie chart, though, is it the final answer? Absolutely not. And as more data comes in, we're not just tweaking these percentages, we're finding issues with it. And science is a process where we're going to have to tweak this. 30 years ago, this pie chart would have been 90% dark matter, and that's wrong. And then we discovered dark energy in 1998 and 1999. So we may need to revise this again, and there are more discoveries to be made. So this is not some factual be all end all. I'm hoping this is close to final, but we may be making more discoveries and have to tweak this further. But right now, this is called the standard cosmological model. And you see here neutrinos, photons, black holes, not enough of them to make up dark matter. They're a tiny, tiny percentage of this chart. So matching up with the cosmic microwave background is something called the large scale structure of the universe. So dark matter causes this clumpiness we see when we look out in the sky. We have mapped already millions of galaxies. There are likely several 100 billion galaxies in what's called the visible or observable known universe, and they form this pattern called the cosmic web. And the cosmic web, we're able to explain beautifully with computer simulations where dark matter clumps first gravitationally and then attracts ordinary matter into clumps. And in these clumps, then where there's gravitational attraction, you create these clumps of gravitational field that then attract the mostly hydrogen and helium ordinary matter, which then forms stars, galaxies, and planets. And this is known as the cosmic web. And the cosmic web has been beautifully mapped out in not just computer simulation, but in real data now. In our telescopes like the Sloan Digital Sky Survey, we see a map of the sky. And we see this clumpiness. And this clumpiness, we think, is caused by dark matter attracting matter. And then there are these gaps, these great voids, where dark energy is pushing out in an anti-gravitational like way, creating these voids. And I can't help but notice, I don't know if this is a coincidence or does this say something deep, is that the universe looks like a brain. I don't know if it's just, one of God's jokes or something, or a coincidence, or does it tell us something deep about the universe? Because the way that galaxies are laid out are very similar to how neurons, synapses, and axons look like, not just in a human brain, but in many other mammalian or vertebrate brains. I'm not a biologist, and as I said, I have to be very cautious. I'm not trying to make some mystical claim or statement, but it's just, at the very least, it's a very interesting coincidence and definitely worth studying. So what is this dark matter, though, that causes this clumpiness? What is it physically? So we have different candidate particles for what it is. And there are WIMPs, axions, there are all these acronyms. We love our acronyms in physics. And the one of the leading candidates is something called a WIMP, which stands for weakly interacting massive particle. And it is a generic term for our ignorance. It is not a specific particle like the ones we already know and love, like gamma rays and neutrinos and neutrons, things like that. It is a generic acronym. It is an umbrella term for our ignorance. But that being said, there are several models that predict something like a WIMP. And two of them, I only give you two examples here on the left. One is called supersymmetry. In supersymmetry, what we have is the hypothesis that for every particle There is a shadow particle called a supersymmetric superpartner that has a different kind of spin, not opposite direction of spin. It's more subtle than that, a different amount of spin, of angular momentum of spin. So supersymmetry, why is it such a good hypothesis, even though we don't have any evidence for it yet? It's because it's analogous to something we already have discovered, something called antimatter. So with antimatter, the idea, for every particle that has a positive charge, you have one with a negative charge. For everyone with a negative, you have a positive charge. And we've discovered antimatter in the 1930s, a long, long time ago, and we use it on a regular basis in incredibly minute quantities. And the idea behind supersymmetry is very analogous to antimatter. The big difference is that antimatter exists. We discovered it in the 1930s, but supersymmetry does not have any conclusive evidence. Right now, it's just a beautiful model, but without any evidence. But what's beautiful about supersymmetry is that it provides you with at least one natural candidate for dark matter. So maybe you can kill two birds with one stone. Now, another approach that could explain dark matter and give you a natural WIMP candidate is extra dimensions. Imagine there is a new direction in which to move beyond X, Y, Z, beyond length, width, and height, the three dimensions we know. And in order to explain, well, why haven't we observed it? Is maybe this extra dimension doesn't just go to infinity in all directions, but it's curved in some way. Maybe it has a cylindrical geometry, for example. And a good analogy for this is, imagine you're looking at a garden hose. A garden hose from far away will look one-dimensional. But if you look closer, you realize the garden hose has width, so it's two-dimensional. But if you look even closer, you realize, oh, wait a second, it's really cylindrical. It's a three-dimensional object. So similarly, extra spatial dimensions could be out there hiding, curled up on a microscopic level. And this curling up on a microscopic level has an interesting quantum mechanical consequence called the Kaluza-Klein tower, where if extra dimensions exist and have such a geometry, they predict new particles. Bingo, those new particles could be one and the same thing as dark matter. And so on the left here, these two ideas, supersymmetry and spatial dimensions, are two favorite explanations for something that kills two birds with one stone and gives you supersymmetry, extra dimensions, but also gives you dark matter. Now, we don't know what dark matter is. Both of these could be wrong on the left. So another idea is something called the axion particle. And the axion you can kind of think of as like a heavy photon. It's kind of like particles of light, but not really, because particles of light, the photon, have zero mass, and axions would have a very, very small non-zero mass and would interact in gravitational, in a magnetic field, for example. And another way we look for axions is through microwave cavities, RF cavities, looking for a resonant frequency for this new particle. So axions are another idea. And I should emphasize that none of these ideas are mutually exclusive. So it's possible that dark matter is WIMPs and axions and something else. Now, the joke that I often tell my students, if we back up a few slides back to my pie chart, is I think it's silly to think that all of dark matter is one thing. Just like yesterday, we were discussing the entire UAP phenomenon is not necessarily one thing. What if it's aliens plus humans from the future, plus something interdimensional, plus something else? What if it's a mixture and it's not just one thing? Because if we look at atomic matter, it's not one thing. We got quarks and leptons, and we have a whole periodic table of things coming together. Why isn't the dark sector just as interesting? I like to joke with my students that there are aliens out there made of dark matter and there's a brilliant dark matter alien scientist out there who says, I've got it. I've solved the mystery of the missing 5% of the universe. And I call it the proton. Or I call it the quark. And he or she or it or whatever pronoun you like would not be wrong, would not be entirely wrong, because most of atomic matter is hydrogen, which is mostly protons, but they would miss electrons and neutrinos and everything else. And so I think it's really crazy to assume dark matter is only one thing. It's probably an entire universe of stuff that has its own periodic table and its own extra laws of physics to discover. So going back here now to the particle candidates, I only am talking to you for an hour, and so I am only summarizing you a few examples. So if your favorite pet theory of dark matter isn't here, don't think that that means I think it's bad or wrong. I only have an hour, and so I have to summarize what are considered by the scientific community the leading theories. That doesn't mean they're right. I just want to summarize for you the major ideas. How do we look for WIMPs then? So I'm going to zero in on WIMPs, which is only one idea for what dark matter could be, but it's a very generic one. So the idea behind WIMPs is that dark matter is a heavy new particle out there. So how do we look for it? We look for it using three different mechanisms. We look for it using direct production, indirect observation, and what's called direct detection. So what are these three different methods? So one method is the particle accelerator, the collider in Europe, the Large Hadron Collider in Geneva. What it's doing is it's banging together standard model particles. That's what SM stands for, SM, standard model. We bang standard model particles together in Europe and try to make new particles. So far, we haven't found any, except for the Higgs boson. We haven't found anything new. And so we need more diverse approaches, smaller experiments, tabletop, a diversity of smaller, cheaper experiments, and that's what we are moving towards. So we have here indirect observation. That requires a satellite in the sky or at the Earth Lagrange point. We put that in space, and for there we look for dark matter interacting with itself and turning into, converting a mass into energy. So since E equals mc squared, you can convert matter into energy. Particles can disappear and turn into new particles. So what if dark matter interacts with itself and turns into standard model particles that we know and love, like gamma rays or neutrinos? That is called indirect observation. And the third method is my preferred method. Obviously, I'm biased because that's what I work on. That's the direct production method, direct detection method. And that's where you're looking for something that goes bump in the night. You place a detector deep underground to get away from naturally occurring cosmic radiation. And what you do is you look for something that bumps into a standard model particle, bumps into an atom. It's literally like billiard ball scattering, like my little picture here. We're waiting for something to bump into a nucleus. And some dark matter models say dark matter interact with the electrons, but the most common dark matter models say that you have a dark matter WIMP particle that will bump into a nucleus. So we're looking for what's called nuclear recoil and trying to avoid what's called electron recoil. And we have to be careful. You notice my cartoon in the upper right. Why do we have multiple techniques? Because what if one of these techniques, because of some law of physics we don't understand, doesn't work or isn't as good? We want to have multiple techniques. So you can see my little joke in the upper right, a cartoon from the 1880s. We don't want to be like the poor astronomer here at their telescope who's looking in the wrong place. And so even within direct detection, there are dozens, hundreds of different techniques because we don't know what's out there. So we want to try as many different techniques we can. So the technique that I've worked on for years uses the element xenon, the same xenon that's in xenon LEDs and xenon headlamps, headlights for your car. And I worked for many years on the Lux experiment. It's now been disassembled and being replaced with a bigger, better experiment called LZ. And the Lux experiment was deployed deep underground in South Dakota, and that's where LZ will be as well. So we have to go deep underground because we need to avoid naturally occurring cosmic radiation that's constantly bombarding us. So we want to have a mile of rock above our heads. So this is a picture of me with one of my former postdocs and students, Jeremy Mock there in the bright green hard hat. We are standing next to the Lux detector, which is a titanium cryostat. So what a cryostat is basically a giant thermos. So this is a giant thermos to keep the liquid, so it's got a vacuum jacket to keep the liquid xenon cold. So why do we use liquid xenon to look for dark matter? Because xenon has this incredible property, many other elements and compounds do as well, but xenon has a lot of other advantages I don't have time to get into, where when radiation interacts with it, it produces ultraviolet light that you can then detect. So here's a little animation you see here playing on the left now, where you're in this vat of liquid xenon, you create an electric field with a cathode and an anode, you create a giant electric field, and you also have PMTs, photomultiplier tubes, for detecting the ultraviolet light. So now let's say we have a dark matter WIMP particle there, WIMP comes along, it hits a xenon atom. You get a flash of light, but you also get some electrons that are liberated. And then the electric field is used to drag. It's like the vat of xenon is one giant battery. You drag the electrons to the other, to the gas on top of the liquid at top, you get a second flash of light. And the time between those two flashes tells us how deep the event was, and the radial distribution tells us where it was. And that allows us to tell the difference between signal and background. So the results from experiments have been nothing. And I know, so there's been a lot of criticism of like, well, why are we looking for dark matter? We keep finding nothing. Well, it may take many decades to finally find it, just like it took many decades of patience for gravitational waves. So all the results so far have been put on a chart like the one at the left, where you have different experimental results that are just going lower and lower and lower and lower in parameter space, where the probability of interaction of dark matter is probably lower than we thought it was. And so we rule out different models. We've ruled out different claims of detection. Unfortunately, so far, we have been just measuring 0 with increasing probability, increasing precision, I mean 10 to the minus some large number. So why are we motivated to keep looking? So we're building bigger detectors, like Lux has turned into LZ, which is the same principle, liquid xenon detector, just bigger. And we keep drawing these curves lower and lower and lower and lower, and implying that the parameter space, that the interaction probability of dark matter particles is lower than we thought. Why do we keep going despite finding nothing? And it's because of the evidence from astronomy and cosmology I presented at the beginning that is so well motivated, that tells us maybe we're not looking hard enough or looking in the right places. So we also have a natural endpoint potentially, where eventually dark matter experiments become so big and so sensitive, they turn into neutrino experiments, which is good for neutrino physicists, but bad for dark matter, where you're just constantly discovering, where your detector is triggering on solar neutrinos. So there's a kind of a natural ending point here in orange, where we're kind of having to compete, where if dark matter is out there, it competes with other signals from neutrinos. So the last thing, before I'm going to switch gears now to dark energy, but the last thing I want to say here is, okay, so I still haven't connected anything here to UAPs, and I wanted to say that I think that you have all this matter out there. Why not use that as some sort of fuel or propellant potentially? And then you have, just by conservation of momentum, absorbing dark matter and just spewing it behind you without breaking any known laws of physics. Why wouldn't this be part of at least some species out there would think of somehow capitalizing on this stuff that's all over the place? And so I think that in the same way that electricity and antimatter were once useless, right? They were just for fun. I don't know if it's a true story or apocryphal, but allegedly Michael Faraday was once asked by the King of England, what good is electricity? And Michael Faraday said, I don't know, Your Highness, but you'll be taxing it one day. And think of how electricity runs our lives. Antimatter is another example of that. Nowadays, you're injected with a small, safe amount of antimatter for PET scans to look for cancerous tumors. What could happen 100 years from now? 200 years from now with dark matter? I don't have enough imagination myself to tell you. I have no idea what could it be used for. But what if, just like electricity and antimatter, what if dark matter once has an incredible practical application? And what if one of them is something as silly as, oh, you just gather it and spit it out? But I think there's something even bigger here. I would be very remiss if I didn't speak of dark energy, the 69% of the pie chart. Now, I have to caution you, dark energy is not my field of research. I might say something wrong. And in fact, I do hope later on, especially during Q&A, that Eric Davis or Hal chimes in if I say something mistaken about dark energy, because it is tied to Casimir effect. 0-point energy might be the same thing. So I want to caution you, this is not my field of research, but I felt like there is no way I can talk about dark matter without talking about dark energy. No way, because dark energy is 69% of the universe. So I've got to address this. And I made a little joke here, dark energy, right? Dark as in dark side. So I've got Count Dooku from Star Wars here with his dark energy using the Force to produce Force lightning. As you can tell, I'm an equal fan of Star Trek and Star Wars. I don't discriminate. I don't know why people are forced to choose. I'm very centrist when it comes to science fiction. I played with Captain Picard next to Luke Skywalker when I was a child. I don't have a problem with there's no fight in my mind. I love both Star Trek and Star Wars. So Star Wars is very conducive to jokes here about dark energy. I think of Dooku and Palpatine and Mom. And what is this dark energy stuff? So despite the fact that it's called dark, I must emphasize that it's probably completely unrelated to dark matter. Probably a completely different thing. The only reason why it's called dark is because we have no idea what it is. So dark is a label for our ignorance. Dark energy probably has nothing to do with dark matter. There are a couple hypotheses out there that say they're related and they change into each other, but they're very speculative hypotheses. It's probably the case that dark energy has nothing to do with dark matter. So what is this dark energy? All we know for sure, beyond this, we're speculating. What we know for sure is that it is causing the universe to accelerate in expansion. But we don't know, is it what's called a constant dark energy, which mathematically, I'm not going to get into the math, of course, here. Mathematically, that's a so-called W value of -1. What a W value of -1 means is that dark energy violates our intuitive notion of conservation of energy in the worst way. There's always a constant density of it. So even as the universe expands, there's always more of it because there's a constant volume density. And so that's the red line here, an exponential increase in the expansion rate of the universe. In blue is what happens if the dark energy violates conservation of energy in a much worse way, where there's always a greater density of it with time. And then what happens is something called the Big Rip, where the universe expands even faster than an exponential. Craziness. And then there's something called quintessence. And that's the idea that the dark energy or 0-point energy is dissipating over time. And eventually the universe does recollapse thanks to gravity. So we start in this chart here. This is the scale of the universe with time. We have the Big Bang on the left, which was actually discovered, which was developed by a Father Georges-Henri Lemaitre, a Catholic priest. Einstein was initially very skeptical and was eventually convinced that the universe does have a beginning in time. At some point. As Calvin of Calvin and Hobbes would say, though, Big Bang is maybe not as a great name like horrendous space kablooey, but we're trying to understand what is the expansion rate of the universe as the function of time, and that since the Big Bang to today, and try to project it into the future. And in order to do that, we need to know what's inside the universe: matter, dark energy, what percentage of each changes the shape of this curve. How do we know? How do we know about dark energy? I told you how we know about dark matter, how we're trying to know about it. How do we know the universe is accelerating? Where does this claim of dark energy come from the 1990s? And it comes from supernova explosions. So there are many kinds of supernovas, but supernovas that are due to primarily white dwarfs around large partners like red giants could result in explosions of those white dwarfs that we believe results in a constant brightness, a reproducible amount of brightness. So what that means is that the farther away that explosion is, you know how far away it is, because the dimmer it is, the farther away it is. And that's what enabled us to discover, wait, the universe is not decelerating like we used to think in the 80s and 90s. It's accelerating in expansion. So that's very interesting. And one of the ideas we think is responsible for this, again, this is not a fact. It is not established, but we think that dark energy might be one and the same thing as 0-point energy. What is 0-point energy? It's real. It's not science fiction. It's not pseudoscience. I noticed some debunker called Hal Puthoff's work on his Wikipedia page with this as pseudoscience. No, it's not. The famous Casimir effect that I'm sure more than half the people on the call right now know and love is real. It's been established in the laboratory. But I want to make sure for those who don't know to give a very brief primer on what this effect is. So vacuum is not empty. We know this from quantum mechanics, from quantum field theory built on quantum mechanics, that constantly there are particle-antiparticle pairs that are zipping in and out of existence. They're happening all the time, all around us, even in a vacuum of space. Even if you had no hydrogen, no protons, it is not completely empty. You can borrow energy from the bank of the universe and return it. If you borrow it for a tiny fraction of a second, and you can produce particle-antiparticle pairs, you can produce an electron and an anti-electron. So antimatter is related here. Again, you can produce proton, antiproton. Why do they come in pairs? It's because by coming in pairs, it does follow certain laws of physics and quantum mechanics of conservation and symmetry and things like this. So you have what's called pair production. Now, how do we know this isn't just a mathematical tool and isn't real? Well, the classic proof is not the Casimir effect, actually. It's something that goes back decades before, and it's something called the Lamb shift. And the Lamb shift was actually discovered near my home in Schenectady by a physicist taking the train, worked out during his train ride the math behind the Lamb shift. And the Lamb shift is a tiny, tiny change in the orbital energy of an electron around the nucleus, in this case, the simplest nucleus of hydrogen, a single proton. And so the Lamb shift has been measured. And the Lamb shift is a very, very small change. It's much smaller than all the other magnetic effects and everything that changes the hyperfine, fine structure of an atom. And so the Lamb shift is one thing, but then I think more exciting is the Casimir effect. And this is where you have you can get an attractive or repulsive force, depending on the exact conditions, between two metallic plates. And this is caused by the fact that even in a vacuum, you can get particle-antiparticle pairs, including electrons and positrons, popping in and out of existence. Now, I have to stress that this is tiny forces in tiny fractions of a second. We, as humanity, do not know. Maybe Hal and Eric have some classified work they can't talk about, but as far as I know from published papers, we don't know how to scale this up and use this to produce, to use this and capitalize on this in a practical way. That doesn't mean we won't one day. But I have to stress that right now, this is very hard because this Casimir effect is a tiny fraction of a second and a tiny amount of energy. That being said, is that the end of the story? No. So there have been more tabletop tests specifically for the cosmic dark energy, which is not necessarily the same thing as 0-point energy. We don't know what dark energy is. Maybe it is 0-point energy, maybe it's not. And one of the alternative ideas for dark energy is that it's a particle, like dark matter. It's not some energy that doesn't manifest itself as discrete particles. What if it does? What if it does manifest itself not as particle-antiparticle pairs? What if it's not connected to 0-point energy? What if it's something else? And one of the alternative ideas is something called chameleon dark energy, where you do have a particle of a very small mass, a very small amount of energy. And so here's a link to one of the articles. This isn't, again, not my research. I'm citing people I know. And one of the co-authors on this paper is David Moore, not the David Moore who's on the call. I don't think they're related. But this paper here by Ryder Moore, Blake Moore, Grotta, and all is I found very exciting, where they're using tabletop experiments to look for new forces, for fifth forces and new particles. And one potential explanation for dark energy is that, just like dark matter, what if it's a new kind of particle? And I got really excited by this paper. Now, they didn't find anything yet. The search continues, because maybe we haven't found anything yet because the probability of these new particles interacting with ordinary matter is just lower than we thought. So we need to work harder and look deeper. So now I got very excited, though, because if you look at the length scales that are the characteristic length scales that match with the characteristic energy scales for chameleon dark energy, I noticed floating around the internet, we cannot say whether this is factual or not, so I'm going to call this alleged. There are alleged materials from crashed UAPs, that is not confirmed, obviously, that contain a certain type of material called a metamaterial that is often used for photons and photonics for redirecting light. And I thought, and I sent an email to Hal, I'm like, this is a big coincidence that actually at least one of the alleged metamaterials has exactly the right distance microscopically for channeling chameleon particles, not for channeling photons. And I was thinking, what if there's some sort of connection here? Because if I was an advanced civilization, wouldn't I find a way to capitalize on 69% of free energy in the universe? And in fact, what I found really intriguing is that now, as a scientist, I'm thinking back on all the books I read. And I remember in the Isaac Asimov's book that I mentioned earlier, he was talking about experiencers talking about 0-point energy, and everyone was laughing that it's so crazy. And then I realized, wait a second, maybe it's not so crazy. We discovered dark energy in 1999. We've demonstrated the Casimir effect and lamp shift. What if it is not crazy? Because wouldn't an advanced civilization wants to capitalize on 69% of the universe is out there? And I have to emphasize again, I don't know, and I'm not aware of myself as a physicist, any way to make this work. I'm just throwing ideas out here because we don't know how to, even if this is established, like let's say we discover the chameleon particle, I'm not sure how would we turn that into some practical effect that we could use for, I don't know, propulsion or something like that. I don't know. But I think we should think about it, because why would we not capitalize on all this stuff that's out there? It seems to me like a natural propellant or fuel is just hanging out there in the universe, waiting for us to figure out how to tap into it. So I'm going to start wrapping up here. So I'm actually finished in less than an hour. And Rich said we started the session early. So there's going to be plenty of time for questions. So I'm looking forward to your questions as I take my last 5 minutes here in order to conclude. So when we add up dark matter plus dark energy, 95+% of the universe is unknown. Therefore, it is crazy to say, and many physicists have done this and did this in the 1890s. Before we discovered quantum mechanics, we're like, oh, that's it. We're done with science. No new patents. We're totally done. I think it is crazy to claim we are done with science. We are not done yet. We are not done. 95% of the universe is unknown. Now, I want to emphasize, though, that I'm not saying that, we're going to throw out all the laws of physics. They're all wrong. No, because the way paradigm shifts have worked most recently in the 20th and early 21st century is we find corrections. So, for example, is Einstein wrong? No. It's too late for Einstein to be wrong. If Einstein was wrong, your GPS wouldn't work, because it requires relativistic corrections. But is Einstein incomplete? Yes. Is quantum mechanics incomplete? Yes. Incomplete and wrong are not the same thing. So you're not going to wake up tomorrow and discover, oh, relativity is garbage, quantum mechanics is wrong. No, because your laptop and your cell phone work. But that doesn't mean there isn't more to discover. All that it means is that we understand that 5%, our little corner, really well. But it doesn't mean there aren't going to be additions, not an overthrowing of what we know, but additions to what we know. So on the dark matter side, experiments have been ruling out vast swaths of parameter space. So we've already been killing versions of supersymmetry left and right. And a lot of theorists get mad at experimental physicists like me. They're like, you killed my beautiful theory. And I'm like, well, you know, your theory did not describe nature. I'm sorry. And so you'll note a lot of dark matter experiments have been left and right killing off different versions of supersymmetry and clues of Klein because we didn't find anything. Now, my second conclusion, it seems natural to me that any advanced civilization would capitalize on the large energy densities of dark matter and dark energy, one or the other or both, as natural, plentiful fuels to propel interstellar craft. Do we know how to do this as humans? No, we don't, because we have no idea what dark matter is. And dark energy, we have guesses. We have guesses that it's probably 0-point energy, but the math doesn't work out. Maybe it's not 0-point energy. So maybe it's chameleon or something else. We don't know. And so there are major catches, though. So my propulsion idea is very, very speculative. It's way out there. Because if dark matter doesn't interact with anything, it just passes through matter, just like neutrinos. It passes through light years of rock and miles of lead and rock. How would you harness it? It's not electrically charged. You can't attract it electrically. You could try gravitationally, but that's crazy because gravity is so weak. So we have no clue how to harness it. We haven't even found it. What would be the reaction? What would be the reaction you would have? I don't know, because, for example, Bussard ramjets require nuclear fusion. Dark matter doesn't do nuclear fusion. Maybe you could just use it for momentum transfer. So basically just collect dark matter and spit it out the back. But there might not be enough dark matter, despite it being 25%. There might not be enough number density of individual particles for that to work. Dark energy, though, I'm way more hopeful. We know a lot less about that, but I think that it makes a lot of sense that there's got to be a way to capitalize on that energy, especially if it's 0 point, to somehow do something with it. And I would imagine you could do propulsion that doesn't violate any known laws of physics. You still conserve momentum and energy locally and everything. Now, another possibility I've wanted to entertain is that dark matter, by definition, one possibility that I've been toying with is, what if there are naturally occurring clumps of dark matter, and that could explain some UAPs. It's very, very unlikely, though, because dark matter by definition wouldn't interact with light, so you can't see it, wouldn't interact with radar, wouldn't interact with your FLIR camera. So it's very unlikely. And I am becoming increasingly convinced we're talking about intelligent control, not a naturally occurring phenomenon. But nevertheless, I thought I would throw that out there as my last bullet, because you never know. You know, there's earthquake lights, ball lightning. What if there's some form of dark matter that does interact with light, very rarely, and produces some blobs that move around in atmospheres? You know, I wouldn't be surprised if that turns out to be the case someday, but that one's even more speculative. I would say aliens is an easier explanation than that one, because that's so unlikely, since dark matter by definition doesn't interact with electromagnetic radiation. So I think I'm going to stop there. I'm going to stop my, I don't know how to stop my screen share though. How do I stop? Oh, there we go. Stop share. Excellent. All right. And I'm going to restart my video here for questions and answers. So thank you very much.
Well, let me tell you if anybody doesn't know what passion is, we just saw it exemplified in that presentation. I mean, I'm suddenly wanting to come up to your classes in Albany. And I just want to also clarify that I defined that I'm a dark wimp, because both of them are connected to ignorance. So I just became a lot smarter, but at the same time, I just realized how dumb that I am. But anyway, thank you so much, Matt.
I look forward to questions, because I do love answering questions.
Well, we're going to hit you up with some.
Yeah.
Okay. So you're ready?
I'm ready. Hit me.
All right. Using Hal Puthoff's space-time metrics engineering hypothesis, would dark matter represent denser space-time where gravity is stronger like a stellar mass, or would dark energy represent expanded space-time where there is pushy anti-gravity?
Both are correct. Yes, that's absolutely correct. So dark matter, it does is, as far as we know, produces ordinary gravity. So dark matter could clump, just like stars and planets form. There could be clumps even. And so you can create high density areas. That's what creates the cosmic web. But then dark energy has this pushy like effect. And so while dark matter creates the clumps, dark energy creates the voids where you have thousands and millions of light years with, like, one proton there, another proton there, no galaxies, no stars, no planets. So dark matter and dark energy appear to have opposite effects. Now, dark energy is not equivalent to anti-gravity. It has an anti-gravity-like effect. We don't know what it is, though, but it seems to have an anti-gravity-like effect where it's pushy, where gravity is only pulley.
All right. The next question I got is if this question implies that dark matter is in our atmosphere as well as outer space in order for a UAP to operate in our gravity. If dark matter exists inside our atmosphere, could this be Tesla's source of free energy around us?
So dark matter is in our atmosphere. That's a great question. Thank you. So dark matter is everywhere. It's inside of you, inside of me. We like to think of Earth and outer space are two different things. Where is the Earth? It's orbiting a sun, which is going around a galaxy. We are in outer space on Earth. Earth is a great spaceship that has taken us around our sun and through the galaxy. So dark matter is passing through you right now in the same way neutrinos and everything else and natural radiation is. So dark matter absolutely is in our atmosphere. It is everywhere. We like to think of it out there. It's not out there, it's everywhere, because if it wasn't, how would I be able to look for it underground, right? So we think it's going to pass through rock. Now, to your second part about Tesla, I believe that dark energy is a far more likely explanation for free energy, in my opinion, which may be wrong. That's not a fact. It's just my opinion. But I do think that dark energy is a much more likely explanation for getting free energy. And the reason is because, as I said, it's a higher percentage of the universe, and we understand less about it. So there's more. When we learn more about it, maybe that could be an untapped source of energy. That's my opinion, is that dark energy, which is probably unrelated to dark matter, is also everywhere. It's also everywhere. It's not just in the vacuum. It's everywhere right now. We just don't know how to utilize it.
Excellent. Thank you. If dark matter doesn't even interact with light, or presumably regular matter, then how would it be possible to tap into it to bring energy into the regular matter world?
Great question. So the idea is, in some dark matter models, the interaction rate with matter is not zero, but very close. And so the idea is that there is a very small probability that a dark matter particle interacts with the nucleus of any atom anywhere. Very small probability, but not zero. You multiply zero by a big number, because there's lots of dark matter particles, and maybe there's something to this. So like in my own experiment, Lux, now LZ, where we're trying to look for dark matter, the hope is that dark matter has a very super weak interaction where it comes along, bumps into a nucleus. Something happens. It exchanges a Higgs particle, maybe a Higgs boson. It exchanges a particle, because remember, there's no such thing as a collision. When my hand collides with a table, that's because the electrons in my hand are repelled by the electrons in the table. So similarly, when I talk about a dark matter collision, collision means there's some particle that's exchanged. So like your magnet talks to your refrigerator and sticks to your refrigerator, could it exchange virtual photons through the magnetic force? So similarly, if dark matter is out there and is real, it probably has some very low level interaction with real matter. Now, that being said, it's entirely possible that dark matter never interacts with regular matter, and it only interacts gravitationally, in which case my experiments will never see anything. That's very sad. But as a good scientist, I have to admit that possibility. It could be that dark matter is forever beyond humanity's reach, but we're being optimistic. We are doing a hypothesis-driven research that's, let's take the hypothesis, dark matter does interact with ordinary matter, just not very often.
All right. The next question, Matt, is under the theory that dark matter or dark energy could be the means for propulsion, what type of technologies could be employed conceptually for a UAP detection strategy from an intelligence collection perspective?
That's a very excellent question. So for dark matter, what's really nice about that physics, if that's what's being used, is it's a natural explanation for lack of propellant, lack of visible exhaust. Because if it's dark matter, it's not visible to our current sensors. And so it's a natural explanation that means you don't have to throw the laws of physics out the window. Because with UAPs, especially with the Tic Tac video, we're like, there's no means of propulsion. And so we're worried, is momentum conserved? Because right, in a normal rocket, momentum is conserved. You chuck mass out the back. What if they are chucking mass out the back? It just doesn't show up on radar and doesn't show up on camera. So something, there's something potentially so it's the lack of signature in that case. Dark energy, the story is much more complicated. Now, I think also, Eric or Hal would probably have a lot more to say about this. With dark energy, that's a potential source of maybe the negative energy that's needed for faster than light Alcubierre, time travel, next talk, things like that. Dark energy might be related to those things. So there's the connection. So dark matter, that's one. Dark energy, very different. I think dark energy might be connected to things like space-time engineering through the pushiness aspect of dark energy. So that's my answer to that question.
All right, thank you. Since CERN and the LHC have been unable to demonstrate supersymmetry, do you think that gives more credence to quantum gravity as the structure of space-time and perhaps the explanation of dark energy? Can you give some implications for what that would mean?
Yes, that's another great question. These are all wonderful questions. So the implications are, so first of all, I should say supersymmetry is a form of quantum gravity theory. We don't like to think of it that way, but supersymmetry through string theory, these are all attempts at quantum gravity. All of them are. So they're not different things. Supersymmetry is part of a family of ideas that are all attempts at quantum gravity. The lack of discovery of supersymmetry at the Large Hadron Collider now could mean there's no supersymmetry, or it could mean that the interaction probability is lower than we think. Now, I'm very biased, obviously, because I work on one type of experiment. I don't want to trash my colleagues who work on the expensive collider, but the experiments I work on are a tiny fraction of the cost of the giant colliders. And so I know a lot of people are upset that since the Higgs boson, nothing's been discovered, nothing else. It's very unfortunate. It means nature is really tricky. Right? There's some that we do know the standard model is broken. We know the standard model of physics is wrong because it doesn't explain dark matter and dark energy. The question is how we optimize cost-benefit analysis, which experiments we build and do. And if I was looking at things, I would say, let's do more cheaper experiments. But again, this is going to be recorded, so I want to put on the internet for 3 minutes. I want to make sure I don't trash my colleagues who do work on the expensive collider, because that also has value. But I personally like the idea of let's build a bunch of small tabletop experiments and do more with less.
All right. Next question is, does Paul Laviolette's theory on subquantum kinetics hold any water? Is it thinking about dark matter? He uses the word ether, but in modern physics terms, not in 1800 ether terms.
I'm not familiar with his work, unfortunately. I don't want to make an ignorant comment then. I'll have to pass that one and I'll have to read up on it later. I do apologize. I don't want to make stuff up on things I haven't read up on.
No problem.
Yeah.
Could some UAPs be made of dark matter?
Yeah, that's what I was suggesting towards the end of my talk. It's unlikely because then they wouldn't interact with light. But then again, maybe those are the ones we don't see, right? Right. So how would you know if they're invisible? So I think it's unlikely, but we should put it on. It should be on the table because I think, like we said yesterday, we need to expand our hypotheses. So what if, some UAP aren't even intelligent craft, but they're just like naturally occurring clumps of matter that we don't understand? I think it's crazy, but we need crazy on the table to make progress. So yeah, ready for the next.
Okay. Particles can disappear and turn into new particles. UFO sightings often include disappearance. Any coincidence?
I'm not sure. That's a really good question. I would be worried because the disappearance I'm talking about means you're destroyed. so I don't know if it's connected, because the disappearance I'm talking about is you would think of as annihilation. So when matter and antimatter come together, this includes dark matter. There's dark matter and anti-dark matter. When matter and antimatter come together, boom, it disappears, turns into new particles. Doesn't disappear completely, but matter turns into energy because E equals mc squared. So I mentioned during my talk positron emission tomography in medical physics. So you're injected with antimatter, a small safe amount. And what happens is anti-electrons hit electrons in your body and then turn into gamma rays. So yeah, disappearance means you don't disappear completely, but you change from matter into energy. So I would be worried if you're disappearing, that the disappearance I was talking about is destruction, essentially, is turning from matter into energy. So that being said, I don't know, maybe there's some way to go from matter to energy where is not destructive, in the sense that then you capitalize on the energy of that reaction. And so I don't want to rule that out, but yeah, there's a lot of cases of disappearance, which is very, very, very interesting.
Okay, the next question for you, Matt, is how much power would you expect from chameleon particles if they are real and a tic-tac sized craft, let's say approximately 40 feet, tapped into them using metamaterials?
Great question. So not much. And that's why I was saying in my talk, I don't know how we would capitalize on this effect because there's so little. So a tic-tac size object, it's like 10 to the minus some really huge number. You could get like a few zeptowatts or something. And according to calculations from Kevin Knuth and Peter and Robert Powell, which we were talking gigawatts. And so the thing is, it's not enough. If my crazy idea holds any water, it's not enough to tap into the natural density of dark energy or 0 point energy, because it's pretty pathetic. Even though it's 69% of the universe on a scale of a few feet, there's bupkis there. So what you need to do is some way of enhancing it, not just tapping in, but somehow increasing the density locally. It's not enough like, I'll just build a giant Casimir plate or stick in some metamaterial into my hull. Unfortunately, the math, at least that I know of, says that's not enough. You would need to find some way of increasing the power because it's tiny. Teeny tiny, orders of magnitude lower than what you actually need. So there's got to be some way to enhance it.
The next question is one we kind of like discussed a little bit yesterday in the panel, but anyway, I'm gonna broach it again with you. Why do you think some scientists struggle with the possibility that non-terrestrial species have always been around on the planet Earth, and ultimately we're just now getting to the point where we can talk about it?
It's our hubris, because we think we're the best thing out there. Peter touched upon this, and Robert with the mediocrity principle and the Copernican principle. We always think we're special. We always think we're the apex, and we are afraid at a deep subconscious level that there could be a civilization out there that is way more advanced than us. Personally, as a scientist who's hungry for knowledge, I welcome that. I am not afraid. I would love it if there are civilizations out there besides our own. Both directions, both more civilized than us, more advanced, and less. Because maybe with the less civilized ones, we can learn from history, the Aztecs, Native Americans, and not come and crush them, but be friendly and work together. And so I think I think that we are so arrogant. We think we know everything and we're the best. There could be so much out there we don't understand. There are trillions, not billions, trillions of potential habitable planets in our galaxy alone. Why do we think we're unique? So I think part of the answer to that question, Rich, is that until 30 years ago, we didn't know about exoplanets. That's part of the answer, is that for centuries, millennia, let's not forget Giordano Bruno getting burned at the stake for being right. There are planets out there, exoplanets. We've discovered 8,000, but that 8,000 is in a little patch of sky this big. This big. If we extrapolate from that little patch of sky, there are probably trillions of planets. So I think the reason why the conversation is changing is in part due to exoplanetary science, which my dear friend Dr. Knuth works on. And I think that that's changing conversation because people are realizing, wait a second, Star Trek wasn't even optimistic enough. Go a few light years, bam, there's another habitable planet. Bam, there's another habitable planet. Bam, there's another habitable planet. I used to think Star Trek was unrealistic. Oh, they found another M-class world. But they're there. They are that plentiful. And that's helping change the conversation.
Thank you. Does the fact that we are made of 5% portion of the universe therefore negate the mediocrity principle discussed yesterday?
That's a really good question. It's actually worse than 5% because remember that of that 5%, it's mostly hydrogen and helium. So we are like the 0.0001%. I don't think it negates the mediocrity principle. Here's the reason why. It's because that tiny fraction is evenly distributed. It's not like, oh, all the crap elements are in the Milky Way galaxy on Earth making human life forms. So the mediocrity principle might still hold because that tiny percentage is everywhere we look. In other galaxy stars, carbon, oxygen, silicon, phosphorus, the periodic table of elements appears to apply. It's not an earthly thing. The entire universe is made of the same elements. So even if they're a tiny fraction, unfortunately, of the big picture, dark matter, dark energy, I think if it's equally distributed, I believe that the mediocrity principle might still be correct. But that is a really good question. I've never thought of it that way before.
Thank you, Matt. Could there be dark matter life forms made of dark matter, possibly possible atoms and molecules?
It's very unlikely, but I don't want to rule it out. So I was joking about my dark matter aliens thing about but maybe not. The key is, here's the key. In order for dark matter life forms to be a thing, first, we would need to demonstrate that dark matter can interact with itself like ordinary matter does. So one of the hallmarks of dark matter is it unfortunately doesn't appear to interact with itself. It appears to only interact gravitationally. So that means it doesn't do electromagnetism, nuclear forces. But that being said, SIDM, that's the acronym for it. You can Google it. Self-interacting dark matter is gaining a lot of traction as a new theory. And so it is possible that if dark matter interacts with itself, that it could form interesting structures. But if it doesn't interact with itself, then it's just, there. And it's just there. But if it does interact with itself, maybe there are dark matter stars. And I mean, I've seen work on this axion stars with dark matter planets. And so I think it's extremely unlikely, but I don't want to say no, because what do we know, right? We don't understand 95% of the universe. So I'm not going to tell you no, because we don't know for sure.
Your slide where you were talking about the fact that much like the universe looks like a brain, if you would, in terms of the synapses and stuff
it
like
does.
that in the brain. This kind of has some relationship to that. Any possible connection between dark matter and microtubules to explain consciousness? Stuart Hameroff and Roger Penrose, Matty Pitcairn has published on the physics realization of the genetic code and the role of dark matter in biosystems. Are you familiar with any of that?
I'm not. The only connection I know between dark matter and biological systems is I do know that there is an effort to look for dark matter in DNA. So there might be a connection because dark matter very rarely could break a DNA strand. But it's very rare because it interacts very rarely. Like I said, it's not interacting with ordinary matter very often. But I do know of work that says that dark matter, because it's always there, will on very rare occasions does create a break in DNA. So there might be a connection, but I'm not a biologist, so I don't want to speculate on things I don't know. Because, you know, you've got like Richard Dawkins, a biologist. He always talking about Big Bang. What does he know about cosmology? He's a biologist. I want to try to avoid talking about things that I have no understanding of, and I'm not a doctor or biologist. But that's the best I can give you. Is if you Google dark matter and DNA, you will find recent serious work by physicists and biophysicists on that will probably better answer your question than I could.
There's I guess somebody was asking, can you expand on the idea that dark matter or dark energy could be a cause of UFOs? I think it's more like, you know, I think you were suggesting that it's more of a propulsion for UFOs. Is that correct?
I was suggesting two ideas. Yes, that's a great question. So I can help disambiguate. Is that I was suggesting two distinct ideas. One is both of those sound like really good ideas for propulsion. And then I had a crazier idea, which is what if there are some fraction of UAP are not intelligent craft, but kind of like earthquake lights, ball lightning is some kind of weird naturally occurring phenomenon we don't understand yet. Still important, still exciting, even if not alien, still some completely new physics to explain how you have dark matter, dark energy sometimes becoming visible, manifesting itself. I think that's so speculative that honestly, aliens using it as propulsion is actually a more credible idea. But I just wanted to throw that out there because I just want to say that let's not rule out any hypothesis. What if there's some way where very rarely dark matter, dark energy, because it's everywhere. It's in our atmosphere, it's in you, it's in me, it's in the earth. What if there's some incredibly rare mechanism where it's no longer invisible briefly? I don't want to rule that out because, you know, that would, and a lot of scientists would find that explanation more comforting than saying, oh, we've got aliens out there.
There's, I think someone had mentioned before about the idea that there, you know, there's obviously these different states of matter and things like that, and the objects seemingly can go through all these different, like the atmosphere, space, and operate in water. And then even somebody said something about, well, what about them going through rock? Is there any evidence in UFO or portal cases for dark matter or dark energy that you're aware of, that a case that might stand out that really might tie more into that? And then, for example, the UFO that disappeared into a cliff of rock. Apparently, there's a case that's like that where it went into a rock. But anyway, any thoughts about that?
Yes, thank you for that question as well. So, as I mentioned during my talk, so the dark matter experiment I work on, that reminds me, I should say, none of the thoughts, comments I'm expressing today, they're my opinion, like Rich was saying, and they don't represent the Lux or LZ collaborations. I don't want to get in trouble because there's still a taboo on this subject. So like if my colleagues on my experiments like LZ and Lux, they find out I was here today, they're gonna be like, oh, Matthew, you've gone off the deep end or something. And so I just trying to say these are my views. But I wanted to mention that I said during my talk, my dark matter experiments, why are they buried deep underground? And that's because dark matter passes through rock like nobody's business. And so to me, that is even a tenuous connection, but a very interesting one that explains not only disappearing into rock, but the multimedium travel and the lack of sonic booms. Because if you're dark matter and you're not interacting very often, you're weakly coupled with matter. You either have no coupling or you're very weakly coupled. That's a pretty natural explanation for not interacting with anything. There's no rock there to you. There's no air there to you if you've got dark matter. So I think that the trouble is then you have to explain, but then why does this show up on radar? Why do you not interact with rock, but you interact with light? And that's a tricky one. That's a very tricky one. It would mean you interact with certain types of ordinary matter, but not others. So I don't see how would we do that. That doesn't mean it's impossible. That would be very difficult, but there's some connection there since dark matter passes through miles of rock like nobody's business. So that's why we deploy our detectors deep underground, because we need to block naturally occurring radiation. Dark matter has no problem getting through that rock.
All right. Well, thank you. Do you think that dark matter is a literal energy field or simply a field in which quanta can travel?
So in the understanding we've come to in physics just in the last few decades is that particle, field, and wave are all the same thing. And we don't know how that's possible, but it's all the same thing. So let's take an example of gravity. we talk about gravitational field and we draw straight lines, right? And we draw a diagram, here's the Earth and blah, blah, blah. And it's very useful. And Newtonian gravity works for the most part. You can use it to get to the moon. You don't need relativistic corrections. But then we just discovered gravitational waves. So waves are involved. What does that have to do with fields? And then what if gravity is made of particles called gravitons? Is that contradictory? No. All that could be correct. And so everything is a field, a particle, and a wave. And so with dark matter, what we don't know is it more particle-like or more wave-like? So, or for example, the WIMP that I look for is more particle-like. You can try to picture it as like a billiard ball. But then the axion that I mentioned, I called it a particle, but you can more think of it more as a wave. And again, with wave-particle duality in quantum mechanics, there's no such thing as particles and waves. Everything is both. Everything is both. And everything is also a field. And in fact, depending on which theories of modified gravity you look at to try to get rid of dark matter, explain it away, if you dig deep, you find out, oh, that modified gravity theory predicts new particles, and we're just full circle back to new particles, and we're back to dark matter. So I think all those things are really the same thing, is that when you look at something enough, it's all those things. And it's just depending on how you look at it mathematically, all of those are just different descriptions of nature, where nature has some just description that we don't have words for in human language. And we're just like the blind monks and the elephant. And we've got the trunk, and we got the leg, and we've got these different descriptions, but they're all parts of this unified whole with quantum gravity that we haven't gotten to yet.
So I share with you, yesterday I was wearing my Higgs boson tie. It had a little pattern for the Higgs boson. Today I'm wearing my UFO bow tie.
Yeah, you've got your flying egg, yeah.
Anyway, could dark energy be a manifestation of time, which keeps us apart from the past and from the future and keeps expanding without changing its density? If then, we would have a W equals -1 component.
That's a really good question. So first, dark energy does seem to be related to the arrow of time, because the expansion of the universe seems to set the arrow of time. So that's very interesting. But I think we would need, in order to properly answer that question, we'd need a full theory of quantum gravity, because right now our understanding of time is that it's inextricably linked with space. And so it's space-time continuum. So masses make those divots that you see on the cover of general relativistic textbooks. But the thing is that if dark energy is a fundamental component of the space-time continuum, if it's the same thing as 0-point energy, then maybe there's a connection there. I can't answer that question well, because I'm an experimental physicist, not a theoretical physicist. So I build things with my hands, with a wrench and a screwdriver. And I build things. I'm more like an engineer than a mathematician. I'm afraid I'm not well versed enough in mathematics to give a proper answer to that question. But I do think that the hint that there might be a connection is the fact that physicists like Sean Carroll, who taught me actually at the University of Chicago, now he's at Caltech, I believe. Sean Carroll always talks about the connection between expanding universe and the arrow of time. And guess what's driving the expansion of the universe? Dark energy. So I do see a tenuous connection there. I just don't have enough mathematics to properly answer your question.
Speaking about that W-1, Eric Davis wanted to share with you that your statement about the W equals -1 is incorrect. You do not understand what the equation of state is. And I'll just go ahead.
Well, our best data shows that the dark energy W is like W1 -1.0000001. So it's like the current data is consistent with exactly -1. So I'm not sure what he means. I'll have to follow up on him.
Okay.
Yeah.
Matt,
go ahead, Eric.
Let me help you.
Yes,
Matt,
go ahead. Jump in.
Do you know what W is?
Oh, yes. It's a ratio of pressure to the mass density, P to rho.
Correct. Okay.
Yeah.
So you said some crazy thing about that violating the conservation of energy and so forth because it's -1. That's not what the equation of state has any relationship to. It's not a conservation of energy thing. It just says the fact that it's -1 means that the dark energy pressure equals the dark energy density equals negative the pressure. Now, where do you see that? You see that in the renormalized vacuum expectation value of the stress energy tensor of the electromagnetic field. When you take the trace of the stress energy tensor of the electromagnetic field, when you do the quantum average in the vacuum state, you get rho equals -P, or W equals -1 when you divide P, when you divide rho by P. So all it's telling you is that that equation of state, W equals -1, means it's vacuum energy. That is a vacuum energy statement.
See, let me clarify what I meant. Yeah, no, you're absolutely right, Eric. Let me explain what I meant. I meant is that because of P over rho is equal to -1, that means that the density goes as a to the 0. In other words, is constant with the scale factor of the universe. So what I meant is that it violates the old-fashioned sense of conservation of energy pre-Einstein from chemistry from 19th century. I meant it violates our, you'll notice my exact wording was our intuition of conservation of energy. But if you look at GR,
Okay.
So in GR,
but just note that's irrelevant because Peebles already has in his book at Physical Cosmology, he's got a chapter on that, and he demonstrates why the expansion of the space of the universe due to dark energy or the fact that it's a vacuum energy equation of state does not violate thermodynamic principles. So you don't want to say it violates old notions. Peebles proved that it doesn't violate the old notions. It adheres to the old notions. He just explains how, and you have to look in that chapter in Physical Cosmology. I can't remember how old that book is. It came out in the 90s or so, and my copy of it is in my apartment in Huntsville, and I'm not in Huntsville. So anyway, okay, so I just wanted to let you know that what that means is that the dark matter surveys, galactic, the type 1 supernova surveys and a few other different approaches of surveys that were taken, all identified W equals -1. The reason why those guys, Rice and Perlmutter, got the Nobel Prize is because they calculated, they estimated from observation that W equals -1 to 5 sigma. So there's been this little discrepancy over whether it's -1 or a little over -1 or just a hair below -1. It seems that they've got a 5 sigma result, and the other approaches turned out to have systematic effect problems and bias and selection bias problems. So they're moving back toward the -1 exactly anyway. Okay, so my statement is also, in addition to that, is what that means is that the positive energy density, according to that data, is attractive gravity, but the negative pressure is what creates the expansion of space. And what people don't realize is that Einstein's general theory of relativity, which overthrew Newton's law of gravity, says that pressure creates 3 times the gravitational force than matter or energy density does. And so therefore, since the pressure happens to be negative in this case, that's 3 times the energy density, positive energy density of dark matter. Therefore, that negative pressure overwhelms the attractive gravitational force of dark energy, and thus, boom, you've got that expansion of space. That is a vacuum energy because it has the equivalent equation of state. You could do that calculation for quantum chromodynamics and find out that the gluon vacuum energy of state equation of state will also equal -1. So basically, that's the same equation of state, W equals -1, that you'll get for a Casimir vacuum. You'll get it for squeezed light. You'll get it for gluons and so forth and so on. And so that's very interesting. So what that means is dark energy is a vacuum energy. A lot of people just don't buy it, and that's okay. They're entitled to their opinions. And so they work their theories to try to convince other people that, no, it's not a vacuum energy, it's something else. Unfortunately, they have been less successful in matching their approach to the observed evidence, to the observational evidence. To roughly even 3 sigma, they can't do well. There have been a couple that have done it up to 4 sigma, but that's still not a good high confidence level compared to the 5 sigma result of a Nobel Prize anyway. So, so dark energy, yes, dark energy is an example for why Alcubierre derived the word drive solution Einstein's equation. He said, hey, we got that inflation, that cosmological inflationary expansion of space-time from the Big Bang up to the period of the recombination 400,000 years later. And after that, we have just steady inflation. Okay, well, can we make the warp drive out of that concept? And the answer is yes. He was looking at the possibility of a dark energy explanation for a warp drive. So you're right. The effective dark energy, though, is really, really, really minute. The energy density of dark energy is a nanojoule per cubic meter of volume, of space volume. The effect of dark energy on the expansion of matter in galaxies or galactic structures and whatnot is 2 meters for every megaparsec. So basically, you're only going to you have to take a ruler the size of 1 megaparsec just to see 2 meters of space expansion. So you're not going to observe dark energy at our scale, at the galactic scale. Probably the distance between, not even at the distance scale between the Andromeda Galaxy and the Milky Way Galaxy. You got to go a bit larger before you could see the effects of dark energy.
Well, that's why I said.
Can we take this offline?
Well, at the beginning, it's all right. It's quite all right, Rich. As I said at the beginning, to my credit, the second half of my talk, I said, hey, if I say something wrong, Eric will jump in. Dark matter is my field, my field, and dark matter I would argue to the end. But no, you're absolutely right, Eric. And I think I said things a certain way because I was just trying to contrast between like Newtonian physics and GR, but you're absolutely right. Stress energy tensor and everything is conserved in the GR sense. It's all hunky dory. You're absolutely 100% right. I just meant that our traditional like 19th century view of conservation of energy is naive, and it needs to be expanded and in order to account for concepts like dark energy.
Yeah. Okay, that's great. And again, you should look at People's book, Physical Cosmology.
Yeah, I know it well. Yeah.
Peacock. I'm sorry, I got the wrong author. It's Peacock, and I don't remember his first name, John Peacock, but it's Peacock. And anyway, he does show you using the first law of thermodynamics a piston model for the expansion of space, and he shows you if you have dark energy or vacuum energy, how that does not violate the law of conservation of energy, even though the energy density of dark energy is constant and its pressure is constant.
Well, let me get back to my other questions.
Guys,
let's go back to my
Can we go back to the questions since this is Matt's presentation?
I have more questions, I think. Okay.
I want to get moving back on. Well, you guys can carry it on privately, but anyway, so these people have paid for definitely coming to this, and I want to be able to get to their questions. So, all right, the next question is, why do you think people report seeing so many different types of objects as UAPs? Could these hypothetical aggregations of dark matter allow people to project subconsciously onto those dark matter clumps?
No, I think there's a simpler explanation than that. My opinion is the reason why there's a variety is because there's a variety of phenomena. So I think that we're asking the wrong questions of like, is it the ET hypothesis or is it this interdimensional? Or next we'll have Michael Masters talking about time traveling humans from the future. What if everybody's right? What if it's all different pieces of the puzzle? And let's go one level deeper. Let's say one particular hypothesis is correct. Let's say extraterrestrial hypothesis is correct. Why wouldn't you have different species with different shape of ship, with different technologies? Maybe some are Alcubierre faster than light. Maybe some are like, oh, screw faster than light. I want time dilation because I want thousands of years to pass by and stuff. So there could be all kinds of different cultures that have different technologies. They have different everything. And maybe there's one technology or culture that's dark matter powered, and another's dark energy, and another does this, and another does that. And I think that we shouldn't assume that one hypothesis is correct. We've been doing this in my field, and it's been making me really angry. That's like, oh, dark matter is one particle. Why? Why can't it be 10 different flavors, just like we are made of, quarks and leptons and this and that? Why can't it be a whole bunch of things? What if everyone is partially right? And so the variety of phenomenon to me implies we're dealing with a variety of answers instead of just one answer. Or like in my example with ET, maybe it is one answer, but breaks up nuanced into sub answers.
Right. Let's see. If 95% of the universe is that question just went away here. Hang on a second. If 95% of the universe is unknown, how can scientists possibly be confident about discussing what happens in the first few seconds of the universe birth, such as inflation theory?
Great question. Frankly, we're not. So there is so much unknown. about the beginning of the universe for just that reason. Inflation theory has very little basis yet. We need a quantum theory of gravity in order to really explain the beginning of the universe. We thought we found evidence of inflation, gravitational waves. Turns out, and this is the good thing about science, science is not about being right all the time. Science is about learning from your mistakes. And we made a mistake. We thought we had discovered gravitational waves. We did for black holes, but not from inflation. In the BICEP experiments, I'm not talking about LIGO, that's confirmed, Nobel Prize, blah, blah, blah. BICEP thought they had the Nobel Prize winning discovery, gravitational waves from inflation. Nope, turns out they saw dust. And so we have no direct evidence of inflation. In fact, the only direct data we have on the universe is from the cosmic microwave background I mentioned in my talk, which is 380,000 years after the Big Bang. So you are 100% correct that we still have a lot of arguing and a lot of debating on what happens in the first few seconds of the universe. It is not a settled question because we have no direct evidence of inflation. We have indirect evidence from observation. We have no direct evidence of what's called the cosmic neutrino background, which comes 0.1 to 1 seconds after the Big Bang. We have not detected that yet. And so there are tons of open questions of what happens in the first few seconds of the Big Bang. After the Big Bang, there are lots of open questions there. Absolutely.
UAP have an affinity to water. Is it? I mean, in fact, there are many cases where they're actually seen sucking water out of the oceans or the lakes and stuff like that. Is it possible that they use hydrogen as a fuel, siphon supplies from the oceans, lakes, and then two, by extracting potential energy available in the field between proton and electron of the atom, then might dark matter be the byproduct? In other words, after hydrogen has been exploited for energy, it becomes more tightly bound and far less reactive, thus rendering it dark.
I'm not sure how you'd convert ordinary matter to dark matter, actually. So I don't know if those are connected, but I do know at one point we were going to have hydrogen cars, and then that never, when I was a kid, we were going to have hydrogen cars, and that never came about. But I do think that hydrogen, is it being not just in water, but being everywhere, right? 75% of that 5% most common element, that does make sense for that to be at least one potential fuel source. Unlike dark matter or dark energy, we know how to harness it. Now, the thing is, I'm not sure you get enough energy for let's say electrolysis or something, separation of water and hydrogen, oxygen. I don't know if that will be enough for the kind of feats that we see and necessary enough fuel and energy for interstellar travel. I don't know. But I do think that that is interesting. And that is an example of looking for common elements in an unknown phenomenon to try to solve it, is you look for commonalities. And yeah, there's all this stuff about water. Another hypothesis I have, just throwing it out there, is even though I said earlier, habitable planets are plentiful, it is possible that a liquid water is not necessarily that plentiful because you have to be just the right distance from the star and how you define the Goldilocks zone. So when I talk about habitable, I mean we have to expand our minds for what that means. You could have life that doesn't need water. But on the other hand, what if water is necessary for all life forms? I don't want to claim that because there could be, I don't know, liquid aliens out there that drink liquid methane, ethane, or something like on Titan. So I don't want to put us into a narrow-minded view like that. But maybe water actually is important for all intelligent life, potentially because of all its great properties and hydrogen bonding and everything. So yeah, maybe there's something interesting to consider there.
All right, next question is, we know that space-time is malleable. Maybe dark matter and dark energy are two sides of the same space-time coin. Is it possible that there exists fluctuations of space-time on the scale of the dark energy and dark matter?
Yes, so I have read, there are models out there, even though I said during my talk, dark matter and dark energy appear to be unrelated. There are models out there like the dark fluid model that say, or the work of, there's also Harry Ringermacher, who's also considers that dark energy and dark matter are two sides of the same coin and are a fluid that change their equation of state, going back to what Eric was talking about, and can change their thermodynamic equation of state from W of -1, dark energy, to W of 0, which is matter-like. And there are ideas out there, absolutely, that dark matter and dark energy are two sides of the same coin. I didn't spend time on it in my talk because it's not the main theory. That doesn't mean it's wrong. There are ideas out there. I just didn't have time to get into that. They are related, and that they're somehow flow into each other, and they're just two different aspects of the same thing. And maybe that's right. We see different phases of matter with ordinary matter, right? Solid, liquid, gas, plasma, high energy condensed matter. There are all these different phases of matter, more than just 3 or 4. There are dozens. Warm condensed matter, hot condensed matter, neutron star matter, and everything. So it's possible dark matter has different phases, and maybe so does dark energy, and maybe they're different phases of the same thing.
In conjunction with the universe being like human neurons that was mentioned, are Fibonacci sequences of shapes seen in the galaxy as well?
I believe they are in spiral galaxies, if I'm not mistaken. So yes, thank you for your question. I hope I'm not. I could be mistaken because I'm not really an astronomer. Dark matter is space related, but I'm really a particle physicist. But if I'm not mistaken, you can make out the Fibonacci sequence within a spiral galaxy, similar to shells of snails.
All right. Can you comment on the holographic principle, also known as extra-dimensional theory, and how dark matter may interact with each other?
Yes, so that's an excellent question. So, well, there's two different things going on there. So the holographic principle is mostly related to black holes, also related to cosmology, where it says you can capture the information about something from 3 dimensions into 2 dimensions, collapse the dimensionality, and get all the information on something out of the surface area. So, for example, with black holes and their event horizons, the entropy scales with the surface area instead of the volume, the famous result from Hawking and Bekenstein. I'm not a theoretical physicist, so I can't go very deeply into it, but I can address the extra dimensions thing. So as I mentioned in my talk, extra dimensions, which are often confused with parallel universes, different things, confused with multiverse, especially in science fiction. An extra dimension is just a new direction to move. Like, let's say we're all living in flatland. So that is connected then again to the holographic principle of 2D and 3D. Let's say we live in flatland. There would be no words in our language for up and down. And there's nothing I could ever say to you to explain up and down. And in physics, we take seriously the idea there are other dimensions. Supersymmetry predicts as string theory. The trick is, though, when connecting with, let's say, the UAP interdimensional hypothesis, the problem is that a macroscopic dimension is hard to explain. Like, why haven't we seen it yet? It's more likely if they're extra dimensions, they're microscopic. What that means is they're rolled up on some subatomic level. That doesn't mean extra dimensions don't exist. It just means they're not like X, Y, and Z, right? The 3 dimensions of space, left, right, up, down, that seem to go to infinity in all directions, but they're somehow, they have some sort of cylindrical geometry. I said this when I mentioned the Kaluza-Klein Tower. There is an alternative that's called the Randall-Sundrum model. There is an alternative, which is that there are large extra dimensions, in which case one explanation for dark matter is that it's ordinary matter hiding in that extra dimension, producing gravity. So I'm trying to be open-minded here, avoid things like confirmation bias, things like that, and try to give you the big picture. There are serious alternative hypotheses here that do connect with extra dimensions, which is one of my favorite things other than dark matter and time travel is extra dimensions.
Oh, you probably have time for like just one more question here. Is it possible that dark energy and dark matter are opposing, so that dark matter surrounds galaxies and dark energy are the shell of the universe?
That's sort of how it works, actually, in a crude way. So dark energy is pushing things apart, dark matter is putting things together. And so, but like Eric said earlier, dark energy really only works on cosmological scales. So for example, dark energy is not going to remove the moon from the Earth or the Earth from the sun. It's not going to, the classic joke is expanding universe is not going to break off your nose, so dark energy, even though it causes universe expansion to accelerate more than we thought. So before discovering it in 1999, we thought the universe we knew the universe was expanding, but we thought it was going to slow down and coast, potentially, recollapse. So what's going on is that the dark energy on large scales. So this is how, for example, why, as Eric mentioned, the Andromeda galaxy, how the hell is that colliding with us in 4 billion years when there's dark energy expansion? That's because dark energy does not negate gravity on local scales, and I put local in quotes, on the scales, even as large as millions of light years, dark energy is not that important. And so gravity is important on those scales. Like between Milky Way and Andromeda, we're getting drawn together. But on the scale of billions and tens of billions of light years, what dark energy causes is that you have these shells, these thin shells, actually of galaxy clusters, almost like bubbles. So cosmic web was one analogy, bubble, and skin is the other analogy I've seen, where you have bubble-shaped structures where galaxies are the skin, and then you have these voids created by the expanding universe. I should emphasize, dark energy does not cause the universe to expand. It's just an ingredient in the mix, in the pie chart I showed, that makes it go faster. It makes it accelerate instead of coast. So I hope that answers that question. So yeah, that's how it works.
Matthew, this has been an exceptional presentation. I've seen nothing but excellent comments about this this presentation, and I just want to say thank you for this. And I think that we're all giving you right now a virtual applause for your presentation.
Thank you.
I certainly am. And again, thank you for this incredible performance, if you would. And we'll look to have you back again.
Thank you. And thank you to Eric. I humbly accept corrections to things I said wrong. I humbly accept correction.
No problem. Okay, well, we're going to be ending this session here because we need to get into the next one. So I'm going to be stopping the recording, if you would, and let's all head to the next session.